Hello, everyone. Thank you for having me as your speaker. Uh, I will try to bring closer the C++ 20 ranges to everyone so that you know what you can generally use now or through outside libraries, and definitely something that you will be able to use in the future when all compilers support them. We will cover which compilers support what later in the presentation. Anyway, here's the general summary what I thought we should cover. Basically, what the ranges are and to see how they work and so on. Uh, what are the changes with the algorithms, which are also kind of part of ranges and mostly not re-implementations. Those are wrappers around old algorithms with new features. Then there are views, which are uh, new and null feature, which is mostly based on functional programming and lazy evaluation and not on standard C++ way of doing things. And well, see what can be done today with ranges, and that's about it. So, what are ranges? Well, it's complicated to answer that question because, well, ranges include also the algorithms and everything, but ranges themselves require knowledge of concepts. So we should ask ourselves first, what are concepts? We don't have enough time to describe everything about concepts uh, in this presentation, but I will try to give you a brief glimpse at what they are. They are, well, of course, a new feature in C++20. I'm not sure if this is best summarized, but this is how I would summarize them. Single failure is not an error is an excellent thing, but well, it's complicated to write, it's complicated to read, and it's complicated to read error messages that come out from such templated um, classes and functions. So concepts try to make that better and easier to use and easier to read if something goes wrong. We will look into one example. For example, we want to draw a function. This is actually an exponent with probably less parameters than it should have to be exact, but never mind. This is a Maclaurin expansion of the exponent function, and we would like to, I don't know, draw a graph or something to evaluate that function. So it's usually written in a double. Okay, no problem there. But what if I want to have differing precisions? I want it in float because that's faster to evaluate, or in long double because that's more precise, or I want to calculate exponent of I don't know, complex numbers, matrices, or whatever I think of. Well, for the first part, we can use concepts to make our function easier to generalize across all floating point types, like this, which is a new thing and nobody will understand, but I will try to explain it. This generally means this is a template function that uses some constraint over a template parameter that says it has to be a floating point, which generally refers to standard C++ is floating point value like it existed since C++ 11. Um, I think that is floating point v is from C++17. Never mind. Well, this is a strange way of writing templates, so we can write them in a more familiar way, or currently, I think most supported way or most readable way, template type name t, which requires something from that t. This is all the same function. There, well, also everything that is written as auto could be t, but never mind. Okay, so now we have a function that would work on both float, double, and long double. What about matrices or complex numbers or anything else that can be multiplied and added? This is a simple way to define a concept that would allow us to multiply elements, add them, and multiply them with some constant. And require that adding or multiplying returns the same type as our matrix or whatever, and multiplying has to be only convertible to, because I don't know, if you put float into a and 2.5 is a double, it will not go nicely. So also this same as and convertible to are new concepts which are introduced into standard library. But this is not an introduction. This is not a presentation about concept. This is just an introduction how one can use them. So now we can write our function with our new concepts and get far less errors when we use it incorrectly. For example, with hello world. If we use our function with hello world, it immediately says you can't use it with multiplication, adding, or multiplication with constants. So we know that it doesn't satisfy the concept scan and then multiply. So we can easily fix the error we had without too much thinking. Okay, well, if we, of course, apply a regular number to our function, we will get the result that we expect. Now, I hope everybody knew already what are concepts, but I tried to approach them, to introduce them in a very fast way so that you can understand. Now that we have a knowledge of concepts, what are ranges? Well, simply said, they are a concept to describe containers that can be iterated and have begin and end, which is naturally not true, because ranges define a lot of concepts. I don't know, bidirectional iterator, forward range, random access, and so on. So it's not really one concept, but the general idea is to have something that can be iterable and has an iterator for begin and an end. Not an iterator, but we'll get to that later. For example, SED vector, which has been around us for, I don't know, since the beginning of STL, is technically capable of satisfying those conditions, so it is a kind of a range. That allows us to constrain our functions and not have to use begin and end, but simply put whatever we want to work with as an argument. Therefore, instead of sorting with begin and end, some random vector, we can sort it with the new ranges sort without begin and end, which is, well, nicer. And, well, most of the things ranges do are compatible with old STL, so you can generally put your range with the begin and end into old STL function, and it should, in most cases, work. I will get back to most part later. Ranges live in a new header called, well, ranges, and they also include new algorithms which are in the old header, well, algorithm. They they have their new sub-namespace std ranges and std ranges views, although there's also a shortcut for std views to point to std ranges views. I'm generally guessing most people will do something like this to avoid writing long names, but I will try to keep full names in this presentation because, I don't know, for clarity or something. Anyway, this is generally what ranges are. Does anybody have questions about containers or whatever I halfly described the ranges are? I am guessing no. So we'll go for the new algorithms. Those are not actually new algorithms. Most of them are simply tiny wrappers around old algorithms, but they are now constrained with concepts so that we can be sure that the arguments satisfy whatever requirements are required by the algorithm in question. For example, has anyone tried to sort an unordered map like this? In general, that is a bad idea, and I don't know why anyone would try that, but I have no idea. For example, this map could have been something else in the code, and sort could have been somewhere else, and somebody changed the vector into an ordered map for whichever reason. Either way, this code will generate 1000 and a bit more error messages, which is a bit more than anyone can parse and get to where they are. Okay, if it was the last thing you wrote in your editor and then try to compile, you can type undo, but if it was not, then, well, you are generally stuck with trying to parse 1228 lines of error codes, and that will be a long time. This is a Godbolt link. On the other hand, if we simply go for range sort, which has constraints with concepts, or if we drop the begin and end because we can, the error message is this. It says, well, requires random access iterator, which doesn't, which unsorted map doesn't have. Also, it isn't sortable. It goes into a bit of details below, but in general, it is relatively clear what the error is, and this is all the error messages that you get, not more. So it is very possible that solving that error will be easy. So to summarize it for now, constraint algorithms allow us to drop using begin and end, thus shortening our code, and make error messages readable and usable. That's naturally not all. Are there perhaps any questions so far? I don't see any questions. Okay. There's a new feature in algorithms called projections. They allow us to have an additional argument for algorithms and to modify which data is being used by the algorithm to do whatever the algorithm does. Anything that can be called, uh, anything that returns something from that data parameter can be used as a parameter for a projection. So any callable. For example, if we want to make a, I don't know, 3D engine and have points with 3 coordinates and faces which are usually triangulated, so they have 3 points. And for whichever reason we never heard that GPU cards exist, and we want to manually sort faces to see which one is closer to camera, which one is further away, so that we can, I don't know which one to hide, which one not to hide. We can do that by sorting, for example, by the coordinate z. We want smaller z values to be first, larger z values to be last. And we decide the point that is closer to us is the one that has any, the faces that are closer is any face that has a point that is the closest. So to sort all faces, we would have to see the minimal z coordinate of every point in every face and then sort by that parameter. So to, for start, see which is the minimum z from all points in one face, we can use something like this in standard C++. Overload the comparison operator and use our own comparator to compare only z coordinates, which is something that everybody has done a million times, I'm sure. If we switch to new ranged algorithms, we can immediately drop begin and end, but everything stays the same. But if we take a look at the definition of a mean element, there's a thing called projection as a last argument. It defaults to std identity, which returns the same thing as it got, and it can be overloaded to be whatever we want. So, as I said before, projections are any function that can return something based on the data that is in the container. So, for example, something like this. We are here finding a minimum element using a standard less, and we are comparing based on the z coordinate of the point. If you looked into the code previously closer, you could have seen that comparator defaults to ranged less, so we can drop it. There is also one catch. This lambda goes into standard invoke, and standard invoke can be called with a pointer to a member, and generally that's the same as simply calling that member from the instance. Also works for member functions, but that's not really important here. So we can change that min element to be a lot more clear now. And this returns an iterator. In this concrete case, we don't really need an iterator, we need a value. And there's a new overload in C++20 that overloads standard min to be able to work with ranges or containers. So we can now use standard ranges min to find simply the minimum point of that face in question. Okay, so now we still have to sort our faces based on what we calculated so far. This is the way as we previously used with standard min. Min element, overload the comparator and use whatever we want inside. In this case, our ranged min for point Z. Okay, but sort also has overload, so we can probably upgrade it. Even if we leave it like this, it's still better than what we would get before getting to C++20. Sure, these lambdas can be dropped outside, but that doesn't really clarify too much of this code. So if we change to range sort, we can naturally drop the begin and end. And just like min element, sort also has a third argument, or a fourth if you use iterator reversion, which can use projections. And just like min element, sort also has a default comparator, so we don't have to initialize it, just leave the curly braces. So we can generally transform the entire thing into these two lines or three, which is probably a lot terser than before that. Here's a Godbolt link if you want to take a look. Only algorithms in the algorithm header have been, well, transformed, constrained, or rangified, however you want to call it. There is a plan to transform numeric algorithms, but that is yet to happen. And I've seen an overall plan for C++23, which might or might not be true. Either way, it doesn't really include ranges in the agenda, so we'll see. Hopefully, numeric will be upgraded as well. Given that there are no questions, I will go to the next section. There are also some views in this new ranges proposal, or, well, not proposal anyway anymore, since it's now included in the standard. Well, views are lazy and relatively cheap, which doesn't mean anything bad. They are lazy because they don't do anything unless told to, and they are cheap because you can move them around for free. They're basically sort of algorithms around the containers that don't do anything can be copied for free and executed only when needed. Views are generally stateless. They contain some data, but that's only data needed to do whatever the view does. For example, if I want to take 10 elements from a container, I have to store 10 somewhere. Usually it is in the template parameter, but never mind, it's still some data stored somewhere. And they also contain a reference to the source view. So they know from which view they were called when you called them. And important to note, containers are definitely not views, but they can be viewed as views by views if wrapped correctly. I would like to show you an example from Haskell that shows how cheap and lazy works. This is a function that filters even members from some list and then maps a square function to the filtered elements. Can anyone guess what this code does? Well, it actually does nothing because Haskell is lazy and doesn't want to do anything unless really forced to. This is the compiled code for the function that actually evaluates even squares and assigns it to some variable. But if you take a look into the assembly output, there are some quads, some jumps, several instructions. Well, actually only a few jumps and moves. Either way, there is no sign of squares or vectors or anything being done. So this is what lazy is. This function which prints the even squares will actually print it because someone wants to use the result of the lazy evaluated even squares. So only when there are consumers for whatever is given to the function, then when will the function actually evaluate. Here's the Godbolt link if you want. Now in C++ 17 or something, we can write mostly the same functionality by these two functions. We remove elements that are not odd because we want only that are not even. We only want even squares. We can erase whatever is not remove generally doesn't remove anything. It simply moves it to the back of the vector. So we have to remove it from the vector if you want to have a regular vector. Either way, after that we can transform the vector and square it. And in our print function, we can apply those even squares and print it out, print the vector out. But this approach actually damages the vector. When I want to print even squares from my vector, I usually don't want someone to destroy my vector. So that's kind of a problem. Okay, I could copy a vector and then pass it to the function, but should I? Or the function could copy the vector and then apply whatever it applied, but still, that's an operation more than is needed. In this approach, even squares actually does things. Here's the assembly output. I don't really understand everything that there is. I see there are jumps and adds and whatever. You can take a look if you want on Godbolt, but either way, it is clear that it probably also it is quite an efficient code. On a glimpse, the only function that is called is memmove. So everything else has been inlined, which is excellent. Either way, this function actually does transform the vector. So that's it. Total number of lines in this Godbolt is 177, 67. Well, number of assembly lines, I didn't mention that. If we transform this into views, which have filters and transforms and several other operators, we can apply the filter to see only odd numbers, see only even numbers. We can to the vector. We can also apply the transformation to see only squares from the either vector or in this case our even input even already filtered even numbers, and then return that to our print vector, which then will print that out. In this case, the function even squares, I don't know what it does, but it definitely doesn't do anything with the vector because this is only several moves and the return. In the end, the total number of lines is 66, and which is 2.5 times less than in the previous example. Keep in mind the result is the same. The even squares are being printed out, so that's about it. Well, if we want to add, we can also add a const to these functions, because unlike previously, these functions don't change our vector. That doesn't really change the total number of lines in assembly, but it is nicer to know that parameters of the function are not being changed when they are not being changed. And now in views, there's a special new operator which allows us to compose views, but not views that are initialized with all parameters, but views that are missing a parameter, the source range parameter. So we can transform these even squares into sort of piping the vector into the filter and then piping all that into transform. And of course, print it out just like before. But vector is, as I said previously, not a view. So how does it work if this operator works on views? Well, a vector actually gets wrapped in a by under views all, which addresses all elements of the container. It gets wrapped as a reference view, as a basically pointer. So it can act as a view even though it's not a view. But if these are all just views, we don't really need the first view. We can leave it in the print vector. So we can transform this into an even squares function and pipe the vector in the ranges copy. but this even squares function is not truly a function. It simply returns the same value every time it's called, and it doesn't take any parameters. So it is basically a constant. Therefore, we should make it a constant. And now we are getting to the point where this is actually almost sort of equivalent to what we wrote previously in Haskell. Lazy evaluated some form of algorithm that is to be applied to some form of container, or without arguments in Haskell, never mind that. So what is the point of these views? Lazy evaluation allows us to freely stack, well, obviously not an infinite, but some amount of algorithms together and not do anything about that unless it is needed. So when we iterate around some chain of algorithms and some form of container, only the items that are being consumed are going to have their algorithms executed on them. But this lazy evaluation doesn't have memory. So if you call an algorithm 2 times, 3 times, infinite times, you will execute everything all over again. Sorry, there was a question if the view is valid if the vector is updated. Well, the view is holding a pointer to a container, so whatever you do to a container is completely not related to the view. When you execute the view and when you read from it, the new values will be shown. So yes, the view is still valid, but it will only show different values when next it is executed. No problem. Well, we want to see how the execution goes with ranges and views. So I've modified the previous functions to print out something when they are being executed, to see when they are actually being executed. In this case, sorry. First, the first from the container is read 1. It doesn't satisfy the first filter even, so the filter goes on and takes the second element, which satisfies that. So it is even. Then the square squares it, and the 4 prints out. Next, even doesn't satisfy, even satisfies, and so on. You get the point. But what if we try doing a for loop around those same squares twice? We get absolutely everything executed twice, which is in this case irrelevant since it is very short, but in every real case, this will be disastrous. We can somewhat minimize the effect if we first store the range into a value because it will remember where it stopped, but only the first view. And I'm not really sure whether this is in standard or just an implementation feature. First time it tries even 1, second times it starts with even 2. So that's some kind of optimization, but it definitely isn't an optimization that is helping anyone the algorithms run faster. So what can be done about that? Well, since the views are lazy evaluated, the only way we can fix the issue is to evaluate them imperatively. For example, like this. We have all the same algorithms and views, and then we simply copy the result into some vector, and well, I didn't show this. And then when we go through it the next 2 times, we end up with an algorithm that first executed the views and then the for loops. So if we need to store the result for further anything of the views algorithms, it is best to manually copy it to some new container and then store it for further use. Well, I did mention containers are not views. Our std vector was actually wrapped by the views all, and which returns a reference. This is a typo, this should be F, but never mind. Ref view, and views don't hold data. That is because they have to be cheap to copy or able to copy in a linear time. Well, so I wrote again the same, probably copy paste, either way. So ref view doesn't hold the vector, it only has a pointer to it. Which brings us to the next example. For example, we decide that we don't want to have manually set vector, but instead we want to pass it directly to even squares. This is not something that will work because this is not the best error there is, but only all L values can become views because they can have the address and be stored as a pointer or perhaps a reference in some implementations. I don't know. R values are not stored in memory, they are temporary variables, and you can't point to them. So since views can't hold any data, they can't actually work with R values. Well, there were some questions, so I will take a look. What were the questions? Is the view still valid if vector? Yes, I answered that. So we never allocate the buffer for the final result, the filtered then squared array. It's all done on the fly. Yes, if it's all done on the fly, not on the entire buffer, but on element per element basis. and the iterator is iterating over whatever is filtered and squared. How easy can you debug issues? Well, I have no idea. Probably a lot easier, since you probably mean because views are lazy evaluated, so you don't really know when they will be executed. Well, you can always use the approach to have, where was it? To have them print out when they are being used, and use that for debugging. Or naturally, you can always step through your code just like with any debugger. Do you pass errors through the piped algorithms? Well, no, you don't. If the algorithm doesn't work, it will, I don't know, throw an exception or do something and quit the work. It's basically as if I called an iterator and then that iterator failed. It's not some pipe that works somewhere in the background and never shows up. The pipes are executed when I when I dereference the iterator. Well, sorry, I think I clicked something bad. Well, okay, here we were. Have I mentioned infinite ranges? Ranges, as I said, have begin and end and are iterable. For example, std vector. But unlike std vector, they have they can have two iterative types. One type for begin, the standard iterator, and the other one for the end. So what then is range? Actually, it's a concept of something that has begin and an end. So what's begin? That's an input or output iterator, basically something that is incrementable, dereferenceable, and so on. Nothing special. This is standard iterator, only constrained into concepts, as I said. So what about end? It's not an iterator. It's a sentinel for the iterator, which can be many things. What is now the sentinel? Well, it's a semi-regular input or output iterator, whatever all of that means. So semi-regular means that's a copyable type, and it can be default initializable. Okay, that's clear. What about weak comparable? Well, it means it can be compared with the other iterator. If you remember, the sentinel was sentinel is for the other iterator, so it can be compared with a regular iterator comparable with iterators. You can copy them around, initialize, increment, and that's about it. Well, not. You can also write a code that, if you don't stop it, breaks your computer, or actually it doesn't. It simply does nothing for a lot of time, like this. So sentinels are objects that are comparable with iterators and enable us to make infinite loops, which hopefully we know will end in some other way, or infinite data streams that can be consumed until the consumer is satisfied. Basically, sentinels are kind of iterators, but not in the same sense as the old iterators. That's optimization that can enable people who make new iterable objects to, I don't know, easier create their iterators, or it enables you to make something like the above for infinite for loop when you know what you're doing and will not run into the situation that this runs infinitely. And the sentinels are one of the reasons why views and ranges are mostly compatible with old school STL. So if you want to use old STL, there is a converter that can help you with that and converts your view into a common range with guarantees that iterator and sentinel are the same type, which they usually are. So now if you run that IOTA, which is a standard IOTA algorithm, but transformed into a view, and I don't know, square every element and take first 50 elements, that will be, you will be able to use that in old STL algorithms. So are there any questions? I saw someone mention Boost v3. Well, Boost v3 includes C++20 random number. It's the precursor of all ranges, so it does include everything that is in C++20 and a lot more. So range v3 is pretty good. Do we also have ranges for rbegin and rend? Ranges have various iterators, so it shouldn't be a problem, but why would you use ranges? Oh, ranges, yes. Well, ranges are simply, I was talking about views. Ranges are basically a concept around standard containers. It's not anything new. It's just how to specify what happens with what already existed. Priv to end, I'm not sure. In case of unreachable sentinel, it is probably well, it's not probably, it's very sure that you can do that, but in most cases, for example, as I said, in STL vector, which is technically a range, you can do previous to an end because you always could. So it depends. In common ranges, you can do that. In some other ranges, perhaps you can, perhaps you can't. Well, Current status of the ranges, they are currently supported only by GCC and newest version 10 point something. If I heard correctly, Microsoft Visual Studio will start supporting ranges relatively soon. So I don't know, watch updates for Visual Studio. And as for CLang, I have no idea. It does support everything. Well, CPP reference didn't say it does, so and I don't have Windows, so I didn't check. But if you don't have GCC or MSVC, there are alternatives. The before mentioned range v3 library, which is made by the guy who actually started the whole ranges thing. So it's a proto-range library if you want. And it supports all standards and supports a lot more than just C++20 ranges. It has features that will hopefully be included in C++23 or later versions. There's also Casey Carter's version of, well, STL2. It is implementation of the proposal that was actually included in the standard. It runs on C++17, and that's about it. And there's Tristan Brindle's Nano Range. Well, it also a C++17 implementation of ranges. It supports all compilers and can be included as a single header in Compiler Explorer. On the other hand, the previous two implementation can be included as options. Here are some useful links if you want to take a look at. The one ranges proposal is what was actually accepted in the standard. There's a draft of the C++ standard, and there's a ranges proposal from back in 2014, which is also interesting to read. There are C++ reference links to ranges and algorithm ranges, and that would be it. Do you have any questions?
Is there anything missing from ranges v3 that you can't do with C++14 or 17 that you can do with C++20, or do you get it all if you use ranges v3?
Well, ranges v3 includes a lot more than is in C++20, so no, nothing is missing in ranges v3. So if you want, you can safely use only v3. You'll lose nothing if you use it instead of C++20 ranges, but it's probably better to use what's in the standard, and there are other libraries that can add certain things if you need them. Of course, if you really need full support for ranges which might come in C++23 or later, then it's probably best to use ranges v3.
Thanks.
No problem.
Thank you, Filip, for the great talk. And if anyone has any other questions, feel free to unmute yourselves and ask. Have a pretty quiet group this evening.
So can you do stuff like using ranges for like reading from files or like reading from stand-in? I mean, sorry, using views to like do like lazy evaluation of like file reading and stuff.
Yes, of course. Well, in my opinion, views are not really fully capable for everything as they will be in the future. But since a file system, shall I say, containers are actually also ranges, yes, you can filter and whatever you want your file system without a problem right now. I mean, if you have GCC 10 point something, or if you use, I don't know, ranges v3, or obviously if you have Microsoft Visual Studio.
Cool, thanks. Yeah, it sounds like you could do some cool stuff like building up some image processing algorithm and then like build it up and then press run or something. So it looks like sounds like there's lots of possibilities.
Yeah, there are, but I don't know. Simply keep in mind that if you are going to execute something multiple times, it's probably better to save the result first. I mean, image processing is time consuming. So if you are applying the same algorithm to multiple files, that's cool. If you are applying it to, if you are reading from the same applied something multiple times, then you should probably copy it to somewhere before using it multiple times.
Can views be
Another
changed?
question popped up in the chat.
Oh, sorry.
I don't really hear what the question
Oh,
was.
it's okay. It's just
I was giving the priority to the one in the chat, but my question is, can the views be changed at runtime? Let's say I create or arrange a view in one function, then I pass it somewhere else, and then at some other place I append few more steps to it, or are they purely compile time things?
Well, you can have some stacked views somewhere and then stack them with some other views. They are not purely compile time in that sense, but I didn't really understand. You think if a user inputs something, I don't know, says, yes, I want to filter squares, then apply the view. I mean, views are really cheap. The views you've made are compile time, but when you they're like, I don't know, const expert or inline and everything. When you actually execute them is when they're being executed. So
Yes. So I mean, let's say you have like 4 views or ranges. So I forgot which one is which, but you pipe them into each other with the pipe operator. And let's say you take first 2 and you assign them to a variable, and you take a second 2 and assign it to a variable, and then you pass them as a parameter to something else, to a function. And in that other function, can you then again join these 2 with a pipe and get a like meaningful result? Or by converting the first view into something that is a variable that has to be passed somewhere else, do you maybe lose some critical piece of context that is only available at compile time?
Well, the views generally live as long as their containers live. If you kill the container, you can't have the view.
Yeah,
But,
yeah, okay. So I guess the question is, can I create one view and then execute it several times against different containers? Or are they like
yes,
hardwired?
of
Yeah,
course, you
yeah,
can. I
yeah.
have some view and then 5, I don't know, containers which are similar enough to work with whatever algorithm I created. And yes, I can apply that same view against multiple containers.
Okay. Okay, I guess I'll have to play with the compiler with myself and find out. Because it reminds me a lot of the link queue queries and pipelines in C# in .NET, only with slightly more like cryptic syntax. So I'm really curious if you could do like nice things with them. Like if you could build the entire machinery on top of them, like the group by queries and I don't know, like joins and such. Like I don't know if you're familiar with the link queue in C#.
No, I'm not really a
Okay.
Windows user, and I don't even use C#. But well, if you try it, you probably can. I don't know. Everything is possible.
Okay, thanks.
No problem.
I'm curious, is there like some other cool operators besides the pipe that can be used to do something cool with the views?
Well, not related to ranges, but that I know of. And I think I know if there's some other operator.
And can you do stuff like if you have two views, like combine them together? Like do like, you know, multiply each element in the view element wise in each view.
There's a join view, but that's not a zip. What you were asking is a zip function from functional programming, and that wasn't included in C++20. It might get included in the C++23 or something. You mean to make, I don't know, two vectors and then chain them into pairs, into vector pairs.
Yeah, or a vector, or like multiply them, or yeah, just that kind of
Yeah,
stuff.
whatever.
Like
Okay, no,
two independent
that-
views over two separate containers.
there's no such functionality currently. There's only a join view, so it will be added soonish enough, hopefully. And well, ranges v3 can do that.
Is it possible to use projections with views? So instead of like passing in a lambda, if you want the view to like extract some element from a structure and then do some other transformation on it, can you just like pass in the same syntax?
No. Unfortunately, no, that's not possible.
Yeah, that would be easy.
It would be interesting.
Yeah. Okay. Yeah, I guess I wanted to test something similar as well. I just wasn't able to formulate.
I think there was another question in the chat from Rossini Andrea. So is the
So actually, like lazy std function, which can be both. So view the combination of algorithms or algorithms plus container. Well, no, view is generally container agnostic. It needs the container as a source of the data, but you basically chain algorithms and then from the outside apply a container. So it's more like, as you said, lazy std function.
So how is it different from range algorithms or filters?
Range algorithms execute immediately. When I say, I don't know, range sort, when I exit to the next line, the container is sorted. But on the other hand, if I, well, there is no sort for views. There might be in the future, but either way, if I filter something from a view, nothing is executed. But when I start asking the view to the new effectively from the C++ standpoint, a container, when I iterate through it, it will start iterating through the original container and asking for elements that satisfy whichever condition I wanted. Or I don't know, there is a take n view which takes first n elements. So if you want to, I don't know, get just quests from these questions, you can say pipe this to take 4, and that will be a new container that from the beginning to the end just has Q, U, E, and S. Well, I have somewhat used ranges, not extremely a lot, but I did use ranges v3 before for the past several years, and well, now I will probably use C++20's ranges or continue with ranges v3 since they have some future features, shall I say. So I'm sorry, somebody asked if I used ranges in day-to-day work.
Okay, cool. Are there any more questions from anyone? Guessing that's a no. So yeah, unless anyone has any
you can
Yeah.
all take a look at the presentation on this link or read the source on GitHub. Well, I think the first link is better. So thank you all for coming and for listening to this presentation. And have a nice evening.
Thank you.